Lecture number 19G, and today we are talking on the three-phase first of all, and then we are going to see how that three-phase is actually going to be giving us the revolving magnetic field. The topics, as you can see over there, our main focus today is actually this revolving field theory. And one thing very important, you won't find the diagrams which I am just going to show you in any of the book. Okay? So this topic, I am going to prove it graphically. In your book, chapter number, I guess, 3. Okay. So in your book, chapter number 3, the proof that is given over there is mathematical. I am going to show you over here a graphical proof so that it's easy to understand, because mathematics is not that easy to understand and analyze it for over here. Now, as I just told you, a three-phase supply is something like this, where there is a 120-degree phase difference between each of the three phases. Now, if this difference, since you can see this difference over here, if this is 120 degrees, if this is also 120 degrees, then this is called as a balanced supply if their peaks are same over there. And in the industry, or if you have a three-phase load, you are always required to have a three-phase balanced supply. If somehow, due to some problem inside your transmission line or your generators or any other problem inside the transmission line, this distance supposedly becomes equal to 110 degrees and this one becomes supposedly 130 degrees. This will still work, but it will have problems. Why? Because here now the balancing is not being done. Now, what I mean by balancing, details will be done in your CAD course, chapter number 16. But here, actually, I want to talk on, if you take this point A, what is this point A? At this point A, my phase A is at its maximum. Phase B is approximately at minus 0.5 and phase C is also at minus 0.5. So, if you add any three voltages at any given point, point A or point B, your answer is equal to 0 over here. Now, I don't know how many of you have taken the lecture of per unit or something, but if you have taken it, you must have an idea what I mean by per unit. By per unit, I here mean that if it is an RMS value, supposedly, then the VA is approximately equal to the peak value of the over here. And for VB, it's approximately 0.5 times your peak value or whatever you are actually having over there. So, whenever you are talking about a three-phase supply, your three phases should have a 120-degree phase displacement and their magnitude. Of course, shape is very important, but I'm not going into that complexity of having a shape differ over there. So this 120 degrees is always going to be there, and the magnitude, either RMS, either peak, they are all going to be same. Then, coming on to how you are actually going to take this three phase and mark it how you. Now in your DC machine, if you remember, you have done this experiment in the lab, that was speed control of DC machine. You run your machine supposedly in clockwise direction, and you wanted to then make it counterclockwise. What did you do? Either you reverse the direction of the armature current or you reverse the direction of the field current. So you were actually changing the direction of one over here. Now in AC machines, I will prove it today also, that your phases, there are three phases, A, B and C. So whenever you are actually going to change the direction of your rotation, you are going to swap any two phases. So what I mean by this, if you see very closely over here in this diagram, I have A phase, B phase and C phase. And you can see B phase is lagging behind A phase, C phase is lagging behind B phase over there. So if I draw these three A, B, C as phasors, you have done this phasors in your CAD too. So if I draw them by a phasor over here, what is this over here? This over here is VAA dash. And what is this VAA dash? Supposedly, you are having a generator. Now, I am representing that generator by an inductor. It can have also a resistance also. So, this winding over here, which I have shown over here in yellow color, this has the two ends as A dash. Then I have a similar B dash over there, and then a C dash. And their common point over there is actually the neutral point over there. And whenever you are actually going to measure the phase voltage, you are either going to measure it from B phase, put a voltmeter with respect to neutral. Or if you want to measure for any other phase, you will take A, put a voltmeter and this one. So these are phase voltages. But if you want to actually measure the line to line, then you have to actually connect two lines over there. Now, when you have represented them inside phasors over there, normally, universally, when you have drawn the phasors, this is your VA or VEA dash, this one is VBB, this one is VCC, because you can see VB is lagging by 120 degrees over there. Now, whenever you want to write down the phase sequence as the word suggests, what is the direction or the ascending or descending order over there. So you are either going to start always in clockwise direction. What I mean by this, here this will be VA, then the next one is VB, and then I continue my clockwise rotation, this will be VC. So my phase sequence over there, as shown over here on this diagram, you can see over here, this is A, B, C. You always have to go in clockwise direction, and this is A, B, C. Now, as I told you, if you want to reverse the direction of your induction machine or synchronous, remember today's lecture is not just confined for induction, it is also for synchronous. Today we are discussing the stator, that is the outer part of your induction motor also and synchronous motor. They both are exactly same in both of these machines. So I will not repeat this for a synchronous machine. So phase sequence over here is ABC. Now over here, if you want to change the direction of rotation, you swap the locations of these two, that is B and C. Now when you will do that, your phase sequence now, this will be VA, this is now VC, this is VB, because you have swapped two. So now if you do the sequence, this is A, this is B, this is C. Oh sorry, A, C and B. Sorry on this. So now this is negative sequence, and there are only two possible combinations available. There cannot be a third one. Why? Because there are three options and maximum number of permutations can be two over there, two orders over there. So this one is the called as the phase sequence. This will give you supposedly a clockwise rotation of your machine, and if you have a reverse of it, this will be giving you counterclockwise rotation of your machine over there. So what is phase sequence? Phase sequence actually tells you when you have drawn the phasors from any direction. Now you cannot say that okay, you have always to start from here, this is A, this is B, this is C. No, you can even write it as first of all C, then A, then B. You only have to move in clockwise rotation. So phase sequence is very important, and when you are going to do a job somewhere in some industry where you have a motor or maybe a generator, this is a common term used between engineers, that what is the phase sequence of the machine over there. So instead of telling you A wali wire jo hai, that is connected with that terminal, B is connected with that terminal, we actually tell the phase sequence over there. So that phase sequence either in positive or either in negative over here, this will actually define that your machine is going to rotate in positive or clockwise direction or counterclockwise direction over here. Now, with this phase sequence, the next thing over here, as I have just told you in the very first start, that a balanced voltage. Not to repeat again repeating, because this is very important, and you will be given some assignment in your lab by Ms. Tarina. I have asked her to actually give you one assignment related to balanced and unbalanced voltages, and you are actually going to measure the power for a three-phase supply, unbalanced or balanced. Here today I am only talking about a balanced one. Reason behind, because an induction machine or a synchronous machine, they both are balanced. By balanced I mean that if there are three phases, all the three phases will be taking same amount of current, same amount of impedance R and X. If they are unbalanced, supposingly if I have a machine and supposingly I have connected it in Y configuration, supposingly this is my machine and I have this impedance over here, certainly this is composed of, and supposingly this is your A, okay, come on. I have this one as A, this is B, and this is C. Now somehow, if the machine is working from the last 10 years or maybe 5 years and it has developed some faults over there, what will happen? Maybe the resistance of B phase is a little less or little larger. Now when this happens, what will happen? The amount of current flowing inside this branch that we can call as IB, and this one as IA, and this one inside over here as IC. Now practically current IA plus IB plus IC should be equal to 0 for obvious reasons, because this was the voltage applied over there. You can see at any point A the voltage was 0. But if the resistance or the impedance changes, then certainly you are going to land in some trouble, and the machine is not going to give you a homogeneous torque. What I mean by this over here, that the machine is not taking balanced currents inside. So this is also a check on any machine. If your machine is not taking IA, IB and IC constant or same value, this means actually there is some problem in your machine. So what will happen when the machine is going to rotate, maybe in the half portion or 2/3 of the portion, the machine is going to give you a torque different, and then the last 1/3 it's going to give you a different torque. So there will be jerks in your motion. So that it will actually tell you that your machine is having a problem inside its winding or impedance or whatever. So today we are only focused on a balanced supply, which means 120 degree phase displaced and 120 degree also for the load also. The load machine is also 120-degree displaced over there electrically. Now, coming on to the next thing, supposedly, if you see this very importantly, two phasors over there, in the first one, there is normal operation. Can anyone tell me the current and the voltage? The current is lagging behind the voltage or leading behind the voltage? Leading the voltage. First, this portion. I'm talking about this one. G. Normally, whenever we talk about phasors, we take the direction in this. We always assume that this is moving in this direction. Phase sequence की बात मत करना यहाँ पे. Phase sequence was we taking in the clockwise direction. So here, if this is VA and this is IA, this is actually telling you that this is that angle theta by which the current is lagging behind. Same thing happening over there. This IB is also lagging behind the VB voltage. And these three currents, IA, IB and IC, these all three are lagging because of this inductance over here inside the circuitry. In any induction machine, you are never going to have any phase difference equal to 0. Why? Because there is a winding. Winding has an inductance, so it's always going to have a phase difference over there. Now, the first diagram, as I just told you, here this angle theta and this angle theta, all these three angles will be same if your machine is same, which means all the three phases, they have the same R and L, this will be same. So this will be telling you that if you add IA vector, IB vector and IC vector, you will be getting 0 output on the neutral over there. So, but if you take is over here for the B diagram, now what is happening in the B diagram? You can see very carefully, IA vector is missing over there. So what is actually happening, that you had a machine over there, and in that machine, supposedly, this was your machine, and this was your A phase, this was your B phase and C phase. Now, your B phase is still connected, C phase is still connected, but A phase is not connected to anyone. So what is happening? If you have not connected any neutral, the current entering IB will be leaving from IC. So what is this is telling you, you can see very carefully that IB vector is in this direction, IC vector is complete negative of that phasor or vector. So if any of the phases of any machine is broken off, the wire is open or something like that, the machine is not going to perform fully, and this current is certainly going to be 0, but this current and this current going inside and out are going to be equal to each other. So in the lab, when you are going to do this experiments of induction machine, please take care that any one wire does not come out, because if it is going to come out, the machine is going to have a wobbling effect, because you are only energizing two phases. The third phase is not there. And as we will proceed in this lecture, you will find out that taking out whole one phase has extreme effects on your machine. The motor is still running. It will still run because of the moment of inertia or because of the motion that is already transferred inside the three phase. So whenever you have a three-phase machine, now whenever you have a three-phase machine, there are two types of connections which you can do. The first type of connection is the, I guess this is a little away. Okay, the two types of connections are Y and delta. I guess you have done this previously also in your CAD 1. You have done your resistor network and inductor network. You have done this one. CAD 1. Anyway, I am just also doing this over here. Now, there are two types of connections for the winding. One is called as Y, other one is called as delta. Now, if you see both of these, they have one thing very different from each other. What is this? Here you have a neutral point, here you don't have any neutral point over there. Now what this means over there? Supposedly you wanted to get at your home, you were trying to get 230 volt. If you have a single phase meter at your home, this power, this one and the neutral, these two wires are going to come at your home and your single phase meter is going to be running. But those homes which have a three-phase meter, they will be having phase A also, phase B also, phase C also, and the neutral also coming in. But again, there will be no line-to-line voltage at your home. आपके पास घर में कोई ऐसी device नहीं है which is going to have under root 3 times your V, A and voltage. Now how this under root 3 times is coming, I will just explain this also by mathematical proof. So over here, whenever a load is connected in a three-phase one, you are always going to connect it with respect to your neutral. But if you are going to connect a three-phase machine in the industry or in the lab, then you are either going to get phase A, phase B and phase C. And if you will connect neutral, this is very important. If you will connect neutral, your machine is balanced. A, B and C phases, they are balanced. Your neutral current, which I can call as IN, would be equal to 0. Because the vector sum of IA, IB and IC, they all are going to be summing equal to 0. But if the machine has a problem in any of the phases, that is IA, IB are same, but IC is a little different from there. So what is going to happen? There is going to be a neutral current and it's not going to be 0. So 4 wires to your machine are required specifically in those machines which have been running for very long and you are going to have some fault, because normally any machine can develop a fault with the passage of time. Maybe the bearing is not good, maybe the windings have been damaged a little inside, the inductance is not correct over there. So either you can have a 3-wire system or you can have a 4-wire system. Now what is the advantage of 3-wire versus 4-wire? You will be dealing this one in your CAT 2 course. Please do ask your teacher to actually go through this one very importantly, because I guess apart from this course and my lecture over here, you will not be talking this one up till approximately the 5th semester or 6th semester. So this is very important. So chapter number 16, please kindly do it very carefully, because I'm not going to talk on this 3-wire and 4-wire. But as far as your home is concerned, you have always 4 wires coming inside your home and you are always having a phase voltage. Now if you focus your attention on this delta, in delta there is no neutral. So this means that practically you can't take the phase voltage over there, because always phase voltage is taken from 1. But if you see very closely, you have an inductor over there and you are taking the voltage over here at this point. So we call this voltage also as VAN also. What I mean by this, since neutral is not existent, we said that the phase voltage and the line to line voltage, they both are same in this 3-phase delta connection over there. Now what is the difference in these two? That difference is going to be evident from the formulas which I'm just going to prove over there. But before I proceed on to formulas, 2 things very, very important. There are 2 things which are just discussed over there. One is called as the line to line voltage, often written also as VL. And then the next thing is either VA-N or also written as simple VA also. So line to line voltage, and this one is also V phase voltage. Any of these 3 or 4 methods are used for representing line to line voltage and the phase voltage. Now, since we have just done that, your phasors are going to be represented over here. This is your VA, this is your VB, this is your VC. Or you can take the positive sequence, this is your VA, this is VB, and this is your VC. Now using these 3 phasors, they are balanced. What I'm going to do, and one thing before, every time whenever you have to draw phasors, please kindly draw them, because you don't have a protector always with you in exam or somewhere. So please kindly try to make them as clean as possible. This angle should be 120 degrees. This angle should also be equal to 120 degrees over there. And you can see how I have actually done it over here. I have taken the 90-degree angle from here and bifurcated it just by simple visual. I have done it into 30 degrees each. So this one's 90 over here plus 30. So this is my VB over here. This one is my VA. And since I will be using VB over here, so I have taken its negative also, that is equal to minus VB over here. And similarly, there is VC over here and then there is minus VC over there. So whenever you are going to draw phasors, this is very important. Phasors are also going to come in this machines course when we shift on towards the synchronous generator and synchronous machines. There's going to be an extensive study on that one also. Now taking this VA, VB and VC, if you see very closely this diagram. Now what I am doing over there, if you just see the phasors over there, look on this VA, this is my VB, this is VA and this VB. Now what I want, this is VA, this is VB. I want to find out VAB, which will be equal to VA minus VB. All vectors or phasors. So over here, I want to subtract VB from VA. So what I have done over here, this is VB, taking negative of it, this will be 180 degree flipped. So this is minus VB. So what I have done over here, this is VA minus VB or plus minus VB. So this is going to be that head to tail rule addition, and then from this central point to this point, this is going to be called as VAB. That is line to line voltage between 2 phases. Here, what was VA? VA was between line and neutral. What was VB over here? That was also line to neutral, but here this is negative over here because VB was here, so negative of that vector is minus VB. So over here, this is minus VB. So VA plus minus VB, this comes out to be VAB, which is actually VA minus VB. So now this blue color length vector is the line to line voltage. And you can see very clearly, I have drawn this diagram to scale, that this VAB is certainly larger than your phase voltage. And this is also evident over there. If I just push on towards the first slide over here of our lecture, here, what was the magnitude of a single phase? If I was trying to find out between this phase A and ground, this was 1 per unit. But if I wanted to try to find out the magnitude between phase A and phase B, then that would be equal to from here till here, instantaneously. So this value is VAB, but this value is VB. So you can see the length of VAB, that is line to line voltage, is larger. So if I go back on that phasor proof over there, over here, this VAB is equal to VA minus VB. Now, we need to find out the length of this VAB. We need some empirical formula. For this purpose, I am taking help from trigonometry. What I have done over here, I have drawn a perpendicular bisector. This perpendicular bisector is making this to 90 degrees angle. So I have now triangle 1 and triangle 2 over there. They both are same triangle. Now over here, can you tell me what is this angle over here? This one and this one. How 30? This angle between VA and VB was 120. This one was 60 degrees. So this angle was equal to also, because they are parallel lines. This one and this one, they are parallel lines. So this is 60. 60 or 120? G. This is 120, alternate angles. This one is 60. So this angle is 120 degrees. This one is 60 degrees. This one is 60 degrees. So when this is 120 degrees, I have two sides of the triangle, this one and this one. They both are same. So the angles opposite to them, this one and this one, they both will be same. So the sum of the angles of a triangle 120. So 180 minus 120 is 60. So this angle comes out to be 30. This angle comes out to be 30. Now this angle 30, I am going to use it for some trigonometric over here. So I need to find out the magnitude of this one. For this purpose, I will take this triangle, supposedly over here, this triangle. Here I have a 90 degree angle. Here I have a 30 degree angle, and here I have a 60 degree angle because it's half of it. So now using this triangle, for right angle triangle over there, what will be this cos of 30? This 30 angle, if I take cos of 30, cos is equal to base over hypotenuse. What is base over there? That is VAB divided by 2. So I have in the numerator VAB divided by 2, and the hypotenuse is equal to VA. So just doing the mathematics and cancelling over there, because cos of 30 is equal to under root 3 by 2, I get VAB equal to under root 3 times VA. So you are getting an expression that your line to line voltage is under root 3 times your phase voltage. And I guess you will remember it after maybe like 1 year or 2 years. You will have to remember it 1.732 and all that, because every time whenever you have a line to line voltage and phase voltage, you have to multiply it by 1.732 to find out the phase or line to line voltage over there. Now you can do the very same proof for the other ones. That is VBC will be equal to under root 3 times VB. Same thing. VCA equal to under root 3 times VC. So you have same things over here like this one. So a generic formula can be written, and that generic formula is this, that line to line voltage is equal to under root 3 times the phase voltage over there. Now over here in this diagram, if I go back on the diagram over here on this one, if this diagram is equal to a 3-phase Y connected load, can you tell me what is this current which is flowing over here, since I have called this one as IB, this current that is flowing over here is IA, and this current flowing over here is IC. IA, IB and IC, they are phase currents or line currents? Dhyan se answer karna. There are two attributes in a 3-phase system, phase voltage, line to line voltage. I am asking over here, in this Y connection, IA, IB and IC, they are phase currents or line currents? They are phase currents because they are flowing in each of the phases. But overall, if you want to find out the line to line current, they are also the same over there, because practically there is no echo. But if you will focus your attention towards this diagram, here this is IA, here this is IB, I guess, and this is IC. So these are phase currents, and they are also line to line currents also, because they are flowing between two lines also. So when we talk about the delta, in delta, this is going to be a little different. Why? What is phase current? Phase currents are those currents which are flowing inside this one. I'm again repeating. Phase currents are this current flowing inside the phases. And these currents over there, if I use another color over here, this one, and this one, they are line currents over here, or line currents over here, or line currents. So in Y connection, over here, your phase current and line current, they both are same. So what I mean by this over here, let me just rub this one and I can write down the equation now. So what I have over here, for Y connection, your line to line voltage is equal to under root 3 times your phase voltage, and your line current is equal to the same phase current. But if you have a delta connection, देखो यहाँ पे आपके पास देर इज एक्चुअली लाइन टू लाइन करंट क्या है, जो एक लाइन से निकल के दूसरे लाइन तक जा रहा है. इफ देर इज नो न्यूट्रल एक्चुअली, सो व्हाट इज द लाइन करंट फ्लोइंग ओवर देयर, दैट इज IB, and then there is IC. Don't confuse yourself with the directions, because they will be having a phase displacement over there. So phase current and line current in Y connection, they both are same as shown over here. But if you have a delta connection, here line to line voltage is the same as phase voltage, and your line current is equal to under root 3 times your phase current. Now I am not doing this proof, you can do this yourself by using the same trigonometric rule. So what you have over here, if you have a delta connection, you have the line current and phase current the same under root 3. If you have a Y connection, then you have this under root 3 over there. Now, very, very important thing which we will be using in the next 2 years also, and in the lab also. Whenever in any numerical or any rated machine over there, if there is written a voltage, supposingly that voltage is written over there as supposingly 400 volt, and there is not written that it's a line to line voltage or phase voltage, it's a universal rule that it's always going to be line to line voltage. This is a normal in electrical engineering. If you are solving any numerical, any nameplate rating of a motor, any industry, आपको कोई engineer भी आपको बताता है कि you have a voltage of 400 volt. So this means he is referring to line voltage unless otherwise specified. वो अगर आपको क्वेश्चन में या वैसे डाटा में आपको बताए कि जी ओके नहीं ये 400 वोल्ट लाइन टू लाइन नहीं है, दिस इज अ फेज वोल्टेज, then certainly you are going to call it as a phase voltage. But if it is not written, your device is a three phase, it always going to be a line to line voltage every time. Okay? Because you are going to solve a lot of numericals of induction machine and synchronous also. So if that question or that statement, if it is not written, this means it's always going to be line voltage over there. Okay, now before I proceed on, I need to find out the total power. But again, this is only for balanced. Now I have two circuits or two types of connections which I can do for three phase. And again, I have just told you, they are only applicable for transformers or motors. They are not available at your home because you don't have a three-phase load at your home. They may be available in the industry, maybe a transformer or maybe a motor. So when you are trying to find out a three-phase circuit, now what is happening over here, if I focus on my Y connection, what is happening over there? If it is a balanced load, the value of current IA, the value of current IB, and the value of current IC, they all three will become equal to 0. If I am going to add their vectors or phasors, because it's a balanced load, because all three voltages are 120 degree displaced, these all three are going to be. Neutral current will be 0 ampere. That's why I have talked about balanced load. Now, when you have IA, IB and IC, their magnitude will be same. Their magnitude will be same because R and L, they both are same. I'm again repeating. If you have a balanced load, IA, IB and IC, their magnitudes will be same. As shown over here in this diagram, I guess where is the diagram over there? I just showed you over here, this one. This magnitude, this magnitude, this magnitude, all three are same. The orientation is different. So what is happening practically, their sum of these all three is equal to 0. That's why neutral current is 0. Now you want to find out the power of your Y connection circuit over here, and all three phases are taking the same current in magnitude. I'm not interested in the other one. So what I need to do, if I only find the power consumed in one phase and multiplied by 3, that will be the three-phase power. I'm again repeating. If you want to find out the three-phase power, if it's a balanced load, you are just going to find out any one phase. So what is the phase current flowing over here? That is IP. What is the voltage phase over here? That is V phase over there. So when you want to find out the power over here, so the power over here for a three-phase circuit will be equal to V phase multiplied by I phase and multiplied by cos of theta. Why cos of theta? Because you have to take the power factor into consideration, and multiply this all by 3. Because they are three phases and they all are taking the same magnitude. Same thing happens for the delta also. Same formula will be replicated over here for this one. So P is equal to, here this will be equal to 3 V phase, I phase and cos of theta. Now coming on to this one, you can see what I have done over here. This one, power is equal to 3 Vp Ip. In Vp is the same V phase, Ip is the same V phase. Now, if it is a Y connected load, listen this very carefully. If it is a Y connected load, we have just found out, just proved it, that VL is equal to under root 3 Vp and IL is equal to Ip. So I can replace in this equation, instead of Ip, I can put IL. And there is 3 Vp, I can put from here VL divided by under root 3. So what will be the formula now? The formula for this one, if I just do this one over here, what is the formula? P is equal to 3 Vp Ip into cos of theta. Now instead of Vp, I can put over here VL divided by under root 3, and Ip is the same as IL, cos of theta will remain the same. This one and this one cancelled and you have under root 3. So what is the power formula now? Under root 3 VL, not Vp. This is VL, IL, cos of theta. So both of these formulas, this one and this one, they both are applicable for your Y connected circuit. One is using phase, the other one is using line to line. Okay? You are going to use this formula, I guess, in the lab also for all the power measurements over there. If it's a balanced load, certainly. If it is unbalanced, then the story is a little different over there. So this one P over here and this P in terms of either the line voltage or in terms of either. Now I leave this question to you. Please find out why the power factor is the same in both. कोई बताएगा मुझे? Power factor क्यों नहीं हमने change किया? Again, sorry? Because line current and phase current, they both are same over there. There is no as such difference over there. So this angle theta and here, they both remain the same. And if you want to find out in terms of Q, because you know active power and then reactive power, then you can replace this one by 3 Vp Ip into sine of theta. This is going to be your three-phase reactive power over there. So I hope you have got the idea. I have tried to touch a little bit into three-phase. There are two types of connections in three-phase. One is called as Y, other one is called as delta. Which one to connect in what condition we will talk about when we are talking about induction machine in journal. But at present, the point over here is this, that all three phases are 120-degree displaced, and if they are balanced, they should have the same magnitude, they should have the same inductance or the resistance of the motor also, then it's a balanced load over there. So this is all your three-phase over there. Now, coming on to three-phase, I will give a small break over here for 5 minutes, so don't worry, just a little bit and then we can have a break so that you don't saturate and I also don't saturate. Three-phase machine. Now, we are going to talk about two three-phase machine. One is called as the induction, other one is called as the synchronous. Now, as the name suggests over there, induction, this means that it is going to be working on the Faraday's law of electromagnetic induction. Second one is going to be synchronous, and the word synchronous actually comes on that there is some electromagnetic locking. Here I have written the two laws by which they are actually going to work. Induction motor is going to work by Faraday's law of electromagnetic induction. synchronous motor or machine. Remember, I have used the word machine over there. It can be motor also, generator also. So for a synchronous and induction machine, the working principles are electromagnetic induction over here, and here electromagnetic locking. Now 70 to 80% of the machines, in fact maybe 90% of the machines in the industry are induction machine. Why? There is very cheap. Induction machines are very cheap as compared to their competitor synchronous machine. And why they are cheap? For obvious reason, if you just scroll down, look over there, there is written speed regulation. I hope you still remember what is speed regulation. That when you add load, how it reduces down. In induction machine, speed regulation is positive. The speed reduces down when you apply load. Now all these fans, whatever, all the machines, motors, which are working on AC, and they are not universal motors just like DC series machine at your home, they are also induction machine, but they are single phase induction machine. Here today I am talking about 3-phase induction machines over there. We will talk about single phase also, maybe in the next lecture I will talk on that one also. But induction machine, the speed regulation is positive. So आप इस fans के, you take out the blades of this fan, the speed will be a little higher. When you have blades over there, you change the tilt of these blades, load is more, the speed will be a little less. But this speed regulation is very, very small, not more than 4 or 5%. In extreme cases, maybe 8%, not more than that. But synchronous machine, since it is working by the principle of electromagnetic locking. What I mean by this, I'm not going to go into very detail because today is not talking on this one. Electromagnetic locking means there is a north pole, there is a south pole. If the north pole moves, south pole will also move with it. So the two poles are locked together. So when they are locked together, you are going to have almost zero speed regulation. So the speed regulation is zero. आप इस machine पे जितना मर्जी load apply कर दो, of course उसकी capacity से ज़्यादा नहीं, it will still maintain the same speed. So synchronous machine, expensive also. This one is cheap induction as compared to it. And the one and most difference over there, in induction machine, it is singly excited. You only require one supply, that is AC, and certainly it will be a 3-phase supply. But if you are talking about a synchronous machine, you will require a doubly excited machine. It's also called as a doubly excited machine because you require AC also and DC also. So today we are talking about the stator of these two machines. That is the outer part, the inner part, which is going to be rotating in form of an induction machine or synchronous. We will talk about in the next lecture. Today we are only talking about the stator, which is common for both of these machines over there. Now, before I move on, what I have drawn over here, two machines. One is DC, the sum we have done before the midterm, and I have drawn the AC also. Now, before I proceed on towards the AC and tell you, what was the problem in DC? The problem in DC was that you were having commutation, there was sparking taking place, and there was a carbon brush involved. What was happening in the rotor? The rotor was having a current carrying conductor, and it has to be provided by carbon brushes. So there was sparking taking place. So this was one of the big problems in DC machine. Secondly, the poles were fixed. As you can see over there, this is the north pole, this is the south pole. Poles were fixed. So when the machine rotated by 180 degrees, you had to change the direction of rotation of current by a commutator so that the machine can produce the same unidirectional torque. So the two problems I have written over there, one is the fixed poles. Second one is that you have to provide the rotor with some current because it's a current carrying conductor placed in a magnetic field. The two problems can be resolved by these two remedies. Make the poles moving, which means that as the rotor is rotating, the poles are also rotating. Now, you may answer over here that here I have made north pole and south pole, and I have, for your information over here, I have made this one as north, this one as south. So maybe I have a winding on this one and I have a winding on this one. So what I will do, at some point time T1, I will keep this one as north, this one as south. Thode time ke baad, I will make this north and this south. After some time again, I will make this north and this south. After some time, I will make this north and this south. And I will continue to make it rotate, in which I am actually moving the poles. But the problem here is it that you are going to have how many poles over there? You have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You have 12 windings and you have to energize those windings by some transistor or MOSFET. Now this technology was not existent when Faraday actually gave the idea of induction machine. He invented AC. So he was actually behind it, that instead of supplying to the rotor by the carbon brushes, why not we induce the EMF inside the rotor by electromagnetic induction? Why? Because in rotor, the problem was this, that you had to supply current to the rotor conductors or the armature. It's also going to be called as armature here also. So what they suggested, the use of Faraday's law to induce EMF in the rotor. So circuit breaker here are removed, or not circuit breaker, sorry, carbon brushes, because also called as circuit breaker, that's why. So this is the remedy which I am going to apply. And what I am actually suggesting over there, that I want something like this. I have drawn this 6 diagrams. You can see what is happening. I am making a north pole and a south pole. In first diagram T1, then there is time T2, then there is time T3, T4, T5, T6. How much angle it has moved, the whole poles are moving. But the problem again surfaces, that is that you have to make windings on each one of these poles, and these poles are going to be energized by some transistor, some microcontroller circuitry. And one for important, back in 1890s, 1805 or 1804, when Faraday actually gave the idea of induction machine, at that time transistors were actually not existent. Nowadays, transistors and MOSFETs or switching devices are existent. So now the brushless DC machine, the electric cars or the normal brushless DC machines in your hard drive or your power supply, all those are brushless DC. What I mean by this, they are actually producing the same 6 diagram configuration by having transistors switching on any one of these. So you are actually moving by DC, switching DC, you are moving north and south pole. But back at that time, 1800s and 1900 in the start, there was no concept of AC over there. So he invented that AC concept and told us that n d phi by dt can induce an EMF inside the rotor. So what he suggested, that you can give 3-phase supply to the stator and produce a revolving magnetic field which is constant. This is very important. We don't want the magnetic field to be variable. We want a constant magnetic field. Why? Because in your DC machine, what was it? You had a field current and this north and south pole was producing a constant magnetic field. Here same, you want a constant magnetic field which is revolving. Now, by revolving, we are doing 2 things over here. By revolving, we are avoiding that commutation problem. We don't need to actually do that shifting of the commutator. And secondly, how Faraday's law of electromagnetic induction work. I have supposedly one winding over here, I have another winding over here. If there is a flux change of this winding, I am going to get an EMF induced in this winding. Simple transformer rule. Now, if I am producing a constant magnetic field over here and there is a winding also there and this winding is moving. So relative I am talking about. So the winding over here or the magnetic field is moving, it will also induce an EMF over there. That will be. So rotor, this is the rotor, this is the stator. So stator is going to move with a constant magnetic field, but it is rotating. So what I am going to do, I am going to make this north and south pole rotating, but by the use of 3-phase. And it will produce a constant magnetic field. So the point over here is this, that by using AC, I am going to produce a constant magnetic field by the addition of A phase, B phase, C phase. I will just show you the plots and everything. And secondly, you are going to induce an EMF in the rotor. And why rotor? Because rotor will be a little lagging behind. They both will not be flowing with the same speed. I will tell you just later on at the last end of this lecture. I will tell you that how the stator and the rotor, they are both going to be running at that time. Any questions up till now? Just like those slides because I have 23 slides and this is going to be a lot. It's very important and it has to be done in one sitting. Otherwise, it's fayda nahi hai. Okay, just one. You can see over here what I have done. Now, instead of protruding poles, yahan kya tha? These poles were hanging below. This one are hanging. And I have not shown the winding. Aap ise winding karenge, then you are going to produce poles over there. Instead of having those protruding poles and windings, what I am going to do, I am going to put slots on the stator. Now, again, if you remember your lap winding and wave winding, we use the word or variable S as number of slots. Here, this is an induction machine, so I am going to use SS as a subscript for the stator number of slots. So what I am going to do, number of poles again P, to number of phases pH equal to 3, and I have SS unknown. I don't know how many SS I have to put on to produce a revolving magnetic field. Now, there are two types of windings in AC machines. Listen to this very carefully. One is called as concentrated, other one is called as distributed. Now, their name actually comes on from the reason that if it is a concentrated winding, the flux is concentrated in one area. How? I will just show you later on. And distributed, you are going to get the flux distributed for a vast area. So normally the machines which you are going to see in your daily life, they all are distributed. But to make the understanding a little, the concentrated machines I am going to also show and distributed also today. Now, if you see over here, I have changed the shape of this slot over there. अभी तक आप लोगों के पास the rotor I was making on in DC machines, I was using a circular. ठीक है, वैसे मिड टर्म के अंदर तो खैर I have got अजीब किस्म की मोटरें आई हैं जिसमें अंडे भी रखे हुए हैं रोटर्स के अंदर and all that whatever I have seen over there. But overall, the shape of the stator slot is very much important in the design. So what I have done over there, you can see, I have changed the shape of my stator slot over here. Instead of circular, I have made it something a trapezoidal. Now, why I have selected 6 slots? This is the question over there. And why they are symmetrical over there? Because this is a symmetrical device. I want 3-phase winding. What is 3-phase winding? I have A, B and C. I have 3 windings to put inside this machine. One is A dash. The other one is B, B dash. Other one is C, C dash. And I'm going to use these 3 colors in all these diagrams. Now, if I am first of all talking about concentrated winding, listen to this very carefully. I am talking about concentrated winding, then I am going to talk about a new parameter which is G. That G is equal to number of slots divided by, in the denominator, I have number of poles and number of phases. Now, whenever you are designing a machine, your customer is actually going to ask you how many poles you want. And remember, just like DC machine, your number of poles are always going to be even. 3 नहीं हो सकते कभी, 5 नहीं हो सकते. It's always going to be 2, 4, 6, whatever. So over here, number of poles minimum can be 2. Number of phases is 3 because I have a 3-phase supply. So when I plug it in this over here, I find out SS is equal to 6 slots. Now this G equal to 1 is telling me that this is a concentrated winding, and these 6 slots are arranged in the 360 degrees. And since 6 slots have to be arranged in 3-phase whole 360 degrees, the angle between them, here this angle is going to be 60 degrees. And I am going to call this one as mechanical angle. Remember, if you remember your formula that we did it in your DC machines, chapter number 7, we talked about this theta electrical equal to P by 2 theta mechanical. This is a 2-pole machine, so theta electrical is going to be equal to theta mechanical. Now what this is telling you, now see this very carefully. Ye bahut important hai. I will just have a break after this one. You have 3-phase supply, A dash, B dash, C dash. You have 6 slots. The phase difference between A and B, kitna hai? 120, and that is electrical. Now you want to convert it into mechanical. We have the expression for this machine that jo bhi electrical angle hoga, it will have the same mechanical angle. So what I am going to do, if supposingly I put A over here, first slot, A dash kahan pe aana hai? This is a question over there. जी कोई मुझे बताएगा why I have put A dash here? I have put A on top, A dash in the below. वो ठीक है, उसे छोड़ो, अभी A dash की बात करो. वो मुझे पता है 120 है बिकॉज जी एनीवे नहीं सिमेट्रिक के अलावा अभी एक हम इसके एक और डायग्राम करेंगे, उसमें भी आप देखोगे इट्स नॉट अबाउट सिमेट्री. द करंट विच इज एंटरिंग ए वी टेक इट एज सपोजिंगली पॉजिटिव, द करंट विच इज लीविंग ए डैश वी टेक इट एज नेगेटिव इफ वी आर गोइंग टू टॉक अबाउट फेजर्स. ठीक है, आप मीटर लगाओगे उसके ऊपर, यहाँ पे आपका करंट सपोजिंगली एज अ कन्वेंशन यू टेकन इट पॉजिटिव, इन ए डैश यू विल टेक इट नेगेटिव. So the two phasors, if you draw it, they will have a phase difference of 180 degrees over there. So this angle over here is equal to 180 degrees, and we have kept it 180 because your electrical angle is equal to mechanical angle. Lekin this is only applicable for 2-pole machine. Why? Because P is equal to 2, you put theta electrical becomes equal to theta mechanical. Then after A dash, you have A here, and then you have B here. This angle between over here is as 120 degrees. Why 120? Because the three-phase supply which you are going to use over here is going to be A, B having a phase displacement of 120. And for obvious reasons, this is B, then this is B dash over here. Then afterwards, from B to C, this angle is again 120 degrees over there. So from C and then C dash, again you have this as 120 degrees over there. So 6 slots are fulfilled here like this, so that A is here, A dash is here, B is here, B dash is here, C is here, and C dash is here. So 6 slots arranged according to this relation, keeping in view that P is equal to 2, you have theta electrical equal to theta mechanical over here. So you are getting this. Now this naming A dash, B dash, C dash, very much important. अगर आप ये गलत कर दो, and one thing very important, before I just give you a break, a few years back, I guess 4 or 5 years back, मेरे पास एक बंदा आया from Bilalganj or somewhere. He was a winder, motor winder, from like he had been winding for the last 3 generations. He used to sit in my class. उसने request करके बैठा था, अनपढ़ था, जाहिल था बिल्कुल. He was nothing. But उसको ये पता था, he knew it that A यहाँ देना है, तो B यहाँ देना है. B यहाँ दे के यहाँ रखना है, C यहाँ देना है तो C यहाँ देना है. उसको क्योंकि उसके बाप दादा ने या बाप ने या दादा ने जिसने भी उसको बता दिया था कि वाइंडिंग करते वक्त आपने ऐसे करना है. But he did not know the reason. You are engineers, you are getting the reason over here. ठीक है? So please understand this thing that A dash, how it is over here. I will show you a 4-pole also just now. I will tell you a 4-pole, but just try to grasp this thing that if your poles are 2, your theta electrical is equal to theta mechanical. So this is A dash, B dash, C dash over here. Any questions with this? So, okay, this was a 2-pole machine and you saw A dash, B dash and C dash windings done. Now, if I change this all to a 4-pole machine. Now see this very carefully. Still 4 poles and G is equal to still 1. Okay, I'm not going to go towards distributed winding. So I have G equal to 1. So if I again put in the formula, now SS becomes equal to 12 slots. Now 12 slots arranged in whole 360 degrees. This is going to give you 30 degrees. So the angle between 2 slots here is equal to 30 degrees and it is going to be symmetric. So all slots. Now, question over here is it, now you have 12 slots, how you are going to have arrangement of A dash, B dash or C dash. For example, again, you have theta electrical equal to P by 2 theta mechanical. Now, since here P is equal to 4, so now theta electrical becomes equal to 2 times your theta mechanical. This is very important now. Because now when you are going to put, supposing the A dash, you put over here 180 degrees. So this will be equal to 2 into theta mechanical, and theta mechanical now becomes 90 degrees. So now the angle mechanical between A and A dash will be 90 degrees. So you can see what I have done over there. Let me just minimize it. You have A over here and at 90 degrees you have A dash. Now, since you have to complete the whole symmetry because now you have more slots than the winding turns. So after again 90 degrees you have an A and then again after 90 degrees you have an A dash. So now there are 12 slots, there are 3 phases. हर phase के 4 conductors आएंगे. And those 4 conductors, this is A dash, A dash. Okay, ठीक है, देखते हैं. So over here, this is A dash, A dash. Similarly, when you have B over here, this is going to be having a phase difference between A and B, 120 degrees. So this one would be now, if I now plug in the values over there, this one would be 120 and this one would be 60 degrees. So now, when you are going to have this one, this is 60 degrees. So this angle A and B. So this is 30 plus 30, 60 degrees. So you can see what is happening. A started here, B is started 60 degrees over there. The only thing that you have to take into consideration that the electrical angle and the mechanical angle, they both are equaling this one. That is theta electrical equal to 2 times theta mechanical. And when this is B, 90 degrees to this one, this is B dash. Then 90 degrees to this one, this is B. And then again 90 degrees, this is B dash. And then again 60 degrees over here, you have this one as again, this is practically 120 degrees electrical, but 60 degrees mechanical. Okay? So I hope you have an idea now what is electrical angle and what is mechanical angle over there. So this is a 4-pole machine. At present I am only telling you how the slots are going to be numbered. Now it's totally up to you. You have a conductor over here as I have shown. A current is going to go inside, coming out from A dash, then going into A, and then coming out of A dash and then going on. So you will have 2 connections coming out and you can give your VA supply at here. So this means that your 2 windings are connected either in series or either in parallel. It's totally up to you how you make the design. So this is a 4-pole machine, concentrated winding with G equal to 1. Now, next thing, if I have a distributed winding where G is greater than 1. Now it can be 2, 3, 4, 5. Higher the value of G, higher is the distribution of flux. So you can see I have taken over here G equal to 2. You can take 3 also, 4 also, but the number of slots will be increased a little. So when G is equal to 2, plug in again the values. This time for 2-pole, SS becomes equal to 12 slots. So now when you are going to arrange 12 slots, this time theta electrical will still be theta mechanical. So now when this will be A, this will be A dash. Then this will be B, this will be B dash over here. Then, sorry, this one is A, this one is A dash, then I have B over here, and then I have this B dash, then I have C, and I have C dash. Now, 6 slots are complete, 6 are still empty. So this is a distributed, which means I am going to distribute the winding. Previously it was 1 conductor. So instead of 1A, I have another A over here. So I have now 2A and 2A dash. Similarly, C dash 2, B and B here, B dash and B dash here, and C over here. So distributed winding means here G is equal to 2 is telling you that there are 2 conductors close to each other, or 2 slots having the same A phase, B phase, or C phase over there. And in practical machines, the number of G is equal to either 3 to 5. So the number of slots are huge over there. So now using any of these 3, now what I'm going to do here, I'm going to use either this one, or I'm going to use this one, or I'm going to use this one, and show you that when a 3-phase supply is applied, how the magnetic field is produced over here in the vicinity of the magnetic, the stator over there. For this purpose, I'm taking 3 phases over here. Phase A, phase B, and phase C. Now this is very, very important. Understand this. Over here, if you see very closely in this diagram, I have taken from time T1 to time T13 timestamps. Each one of them is 30 degrees difference, which means this is T1, T2, T3, T4, T5, T6, T7, and so on up till T13. Why T13 up till? Because this is whole one cycle of A phase, or maybe B phase or C phase. So here I have taken this one T1 at 0, T2 at 30, T3 at 60, and so on up till T13. Now T13 is 360 or 0, same thing, because it's starting from the same point over there. Now for each one of these timestamps, I am going to draw a point in the magnetic field that at time T1, which is at this point, what is phase A? Phase A is 0. Phase B is negative over here. And phase B is positive because it's having a voltage positive. So the 3 values are this one. Phase A is 0, phase B is negative, phase C is positive. So what this means over there, if I have 3 windings, the A winding will be having no current, B and B dash will be having a negative current, and C dash will be having a positive current over here. Now, how to represent it? I have to take one rule over here. If current is positive, I am going to take, for supposingly if this is positive, for C I am going to take a cross, just like you did in your DC machines. Then if it is negative, you will have to take it dot. So the current is positive. So this means you can see over here, if you see very closely over here, what I have done over here for C phase, it is positive. So there is a cross. So current is entering C and coming out from the C dash, so it's a dot over there. And similarly, phase A is empty. What is phase A? This is the conductor here. I have only shown one conductor. Practically, it will be more than one conductor, just like the DC machine. So this will be A, this will be A dash, and here they are empty. There is no current because at time T1. Then for phase B, it is negative. So B is not going to have a cross, it's going to be a dot. And then this B dash is going to have a cross over there. Now, if you see these very thin lines which I have drawn over there for the magnetic field line, each conductor using your right hand rule, thumb pointing out in the direction of the current or out of it, the fingers curled are going to give you the direction of magnetic field. So if you see supposedly this B dash over here, if I can show this one over here, you have this B dash over here. So your magnetic field is here like this. So you can see the arrows over here. The magnetic field is going to be produced here. Similarly, this cross shown over here, this is the magnetic field direction over here. And if I have the C dash over here, thumb is pointing out outward. So I have this one over here like this and similar. Now you can see over here, this magnetic field and this magnetic field, they both are going to have a combined effect of each other because they both are dots over there. These two are crossing. So practically over here, this yellow color magnetic field which I have shown over here is the actual magnetic field flowing when you are at time t1. A phase is empty, so there is nothing over there. But this is the magnetic field coming down. This is the magnetic field coming down. So these two conductors, they are having a cross. So that's why they are having their magnetic field coming down using your right hand rule. And these are dots. So this is the current direction coming down. So at time t1, since we all know in a stator, you have to produce poles. So for that purpose, you have a north pole because the flux lines are coming down from here. So this is the north pole, this is the south pole as shown by this yellow color arrow. So at time t1, now you have a magnetic field of two poles and it is giving you two poles at this orientation over here at time t1. Then next thing, I am now going to go towards time t2. For this purpose, any questions with this G? Time t1 pe we got it, north pole is on the top, south pole is on the bottom. This is at time t1. Now when I will move on to time t2, what is the direction of magnetic field? Now I want to see that. For this purpose, same over here, same case, I have drawn two timestamps over there. One is t2. Now what is time t2? Time t2 is here. Now phase A is positive, C is also positive, but B is negative. So this means when I will plot this one, your phase A is positive, B is negative, C is positive. So now again if you apply this one, your phase A is positive, you have a cross here, a dot in A dash. Phase B, it's negative. So what is going to happen? In B, instead of cross, there is going to be a dot. Then in B dash, there is going to be a cross. C, it is positive. So in C, there is going to be a cross. Here it is going to be a dot. So now you can see very clearly over here, this cross, this cross, this cross. I have shown the magnetic field in their respective colors over there. So now these three are going to have a magnetic field combined effect, producing a north pole here, south pole here. Now previously what was happening, north pole was here. Now it has moved to center of these two slots. And what was the angle between this and this one? 60 degrees. And how much you have traveled over here? You have traveled by 30 degrees over here. And what is the time difference from time t1 to t2? Same diagram over here. That is 30 degrees electrical angle. This angle is 30 degrees. And since this is a two-pole machine, your theta electrical is equal to theta. So this is a test over there that you know already that theta electrical is equal to theta mechanical, and you can see very clearly over there that your magnetic field, mechanical angle traveled by the poles from time t1 to t2 is 30 degrees. And when you do it for time t2 to time t3, now this has moved to this point. So you have 30 degrees traveled over there. Previously magnetic field in time t1 was like this. Now it has moved to this one. So angle traveled is 60 degrees, and time between T1 and T3 is also 60 degrees. So you can see over here, because you have 30 plus 30 electrical angle, 30 plus 30 mechanical angle, that is 60 degrees over here. Any questions with this? So I can proceed further. Okay, Hamza, can we see ये बच्चे हैं इस ग्रुप के हैं, हमें शिफ्ट करना है यहाँ से या नहीं? Just confirm it out. Okay, now I've done this for almost all timestamps so that you are clear on this one. I'm showing this one over here. At time T4, this is having a phase A is having its peak. Phase B is at negative. phase C is also at negative. So you have now at time t4, phase A is positive, B is negative, C is negative. Now you can see over here, by having diagrams drawn over there for each timestamp, I'm not taking their magnitude into consideration. I'm only taking that either they're positive or negative. We will talk about magnitude when we do the mathematical proof. Yeah, we are only concerned that what is the orientation of the magnetic field. So now when I make it A as positive, this is cross, A dash is dot, B and C, they are negative. So this means in B, there is going to be a dot. So here you can see in C, there is a dot, in B, there is also a dot, and in B dash and C dash, I have a cross. So now these three conductors, they are reinforcing each other. They have their magnetic field in this direction. So you have a north pole here, a south pole here. So now at time t4, the mechanical angle traveled up till from time t1 to time t5. If you see this one also at time t5, what is time t5? This is at 120 degrees, because this is 30, 30, 30, 30. 4 times 30, 120 degrees. So at 120 degrees time t5, the orientation of the magnetic field is like this. Now when you have orientation like this, you can see you started from here and now you have come up till here. So the angle traversed is equal to 120 degrees. And same is this. And why this is here? Because theta electrical is equal to theta mechanical, because this is a two-pole machine. Now, I have drawn this one over here for other time periods also. Okay? I will just show them in your video over there. You can apply it yourself. You can do it yourself over there. For time t6, it's here. For time t7, this is actually time t7. Let me correct it over here. So from time t6 and t7, you can see the orientation. The magnetic field is rotating. So time t6 and t7, you can see every current has been written over here for time t6 and t7. And then after time t7, I have not taken over here. I have gone from time t7 to up till the end. So over here, up till time t7, T8, T9, T10, T11. So all of these four are drawn over here. You can see very clearly. Time T8, your magnetic field is here. Time T9, it's still moving. Time T10, it's moving. And at time T10, previously क्या था? Magnetic field ऐसे थी. Now how much angle it has moved? It has moved almost 270 degrees. So time T10, if you just see on this one, from T1 up till time T10, 270 degrees. So theta electrical is equal to theta mechanical. So you have all these angles equal. So at time t11, now the magnetic field. So now only 2 timestamps are left. And now the important thing. Time t12, I am approximately at 330. And then at time t15, I am at 0 or 360 degree. So you can see at time t13 or t1, now the magnetic field is back from where it started. So it has completed the whole rotation, one complete revolution for one complete cycle. Now here is the important thing. Listen this very carefully. From time t1 to t13, one complete revolution of poles where electrical angle transversed is also 360 degree, because number of poles are equal to 2. So what you want to do? Now you have a speed of your applied voltage that is given as frequency. In Pakistan, we have a frequency of 50 hertz. What is this telling you? It is telling you there are 50 cycles per second. Now, what I mean by this? For two-pole machine, listen to this very carefully, one revolution is equal to 360 degrees or one cycle. Now, if that one revolution happened in 1 second, that means that if F revolutions per second were required, you need to give F cycles per second. In Pakistan, that is 50 hertz, that is cycles per second or hertz. Now, this is in cycles per second. If you want to convert it into RPM, that is revolutions per minute, you have to multiply it by 60. So that this is revolution. So what this is telling you, that if you have a two-pole machine, listen to this very carefully, your speed of the magnetic field is given as 60F. 60F is the speed of your revolving magnetic field, which is having a two-pole machine. Remember, this is only for two-pole. Abhi main aage aapko four-pole bhi karta hu. So for two-pole machine, the formula is 60F revolutions per minute. When you are giving 60 over here, f hertz over there. This is actually not 60 over here, so you have 60. F frequency is the applied. So you are applying f hertz in revolutions per minute, you are going to get 60 f. Now, what will happen if I have a 4-pole machine? Same diagram I have taken from the last slide. What was the last slide I told you in concentrated? This was the concentrated over here. This was your number of slots equal to how many? 12. So now you have 4 poles. Now when you are talking about these 4 poles, let me go on that slide again, and I have this one. Okay, 4-pole machine. Now, instead of doing all the timestamps, I'm now going to take only selective ones, so because it can save time. So I'm only going from time t1 to time t3. What is the angle transverse? 30 plus 30, 60 degrees. So now, let's see for time t1. At time t1, what is the value? Let me write it down also, because it's going to be. At time t1, my phase A at time t1, my A phase is 0, B phase is negative, and C phase is positive. So now let's apply this one over here. A phase, you can see empty, 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 empty. There is no cross and dot. But B phase is negative, which means B is going to have a dot, B is going to have a dot, B dash is going to have a cross. Oh, sorry, this one. Because B is negative, so your B is having a dot. Otherwise, if it was positive, there will be cross. So this is dot, this is also dot, this is cross, and this is cross over here. Similarly, C is positive. C is positive. So at time t1, you put C as cross here, C as cross, C dash, dot, and dot. Now, when all of these are done, this is the most difficult part of a 4-pole machine. Now you see over here, you have 4 poles. How? You see this cross and cross. I've not drawn their individual fluxes over there, but you use your right hand rule, the flux direction is like this. So this means flux is flowing over here. This part is empty, it's not producing any flux. Similarly, this is dot. So this will be coming out, fingers curled in this direction. So this is a flux flowing like this. Similarly here, this will be flowing like this over there. So flux is flowing over there. And similarly for this one, this will be like this. So you have now 4 poles. From here north, south. From here north towards south, from here north towards south, and this one. Now this is very, very important in this machine now. How many axes are there? Here there are midterm se related question. Can you tell me how many magnetic axes are here? I'm not talking about magnetic neutral axis. You have a north pole, 2 opposite poles, then you have 2 south poles. How many magnetic axes? आपके पास एक नॉर्थ होता था, एक साउथ होता था. The straight line was giving you the magnetic axis. Here कितने हैं? 4. You have a north from here. This is one axis. This is one axis. This is one axis. This is one axis. You have magnetic axis 4 over here. Now, if you do this one for time t3. Now, what is it at time t3? At time t3, G, what is at time t3? Can you tell me? A phase. A phase is? At time t3, this one is positive. B phase, negative. C phase, C phase is 0. Okay. So now you can see what I have done. A phase is positive. So this is cross, cross, dot, and dot. Then B phase negative. So this means B is going to have a dot, cross, dot, and cross. So now if you apply the same rule using your right hand rule, remember, please always apply the right hand rule. This is very important. So what you are doing over here, this is your magnetic field one direction, this is the other magnetic field direction, this is another one, and this is another one. How many poles it's producing? 4. And how much angle it has moved? Previously, this one was having north pole here. Now this has moved to 1 slot. What was the angle between these 2 slots? Not 60. It is 12 slots, 30 degrees. So how much angle the magnetic field has moved? 30 degrees. How much angle you move from time t1 to t3 electrically? 60 degrees. So this is telling you that by increasing the number of poles, your angle or the speed is reducing. It's halved over here. So now you can do this yourself for the other times. I have done it for time t5 also and time t7 also. For time t5, you can see it has again moved over here. This is north pole, this is south pole, north pole, and north pole, south pole, south pole. So from time t1 to t7, please, from time t1 to t7, from here up till here, what is the angle electrical? 180 degrees, because this is half of the waveform. So this is 180 degree electrical angle, theta E. And if you have t1 to t7, you have 90 degrees rotation. Now, we have to use these two now cases. One is 2 pole, other one is 4 pole. Now, for 2 pole, we find out, okay, the speed was 60 F. Now for 4 pole, the problem is this, that for 4 pole machine, for 180 degrees, if you are having 180 degrees, you are only getting 0.25 of the revolution, which is actually 90 degrees. Because you are getting half of it. Because theta electrical here will be equal to P by 2. Theta mechanical, P is equal to 4. So theta electrical is equal to 2 times theta mechanical. This is a 4 pole machine. So now if I just take this 0.25, this is equal to 1 revolution equal to 2 cycles here of the electrical angle. इन्हीं केस का मतलब ये है, listen this carefully. If I want to complete full 1 complete revolution, how I may require? This is 360 degrees. I will have to move 360 degrees more. So speed is reducing. So the end is this, that for 1 revolution, you require 2 cycles. For 1 revolution, you require 2 cycles. Then for F cycles per second, which is actually the frequency you are providing, you will be getting F by 2 revolutions per second. ठीक है, अभी मैंने ऊपर वाली इक्वेशन के अंदर सेकंड्स नहीं ऐड किया था. मैंने सिर्फ बताया था कि 1 revolution कब होगा? When you have 2 cycles transferred. Now those 2 cycles, if they go on in 1 second, then this is called as F cycles per second. Frequency आप जो apply कर रहे हो. Then you have F by 2 revolutions per second. Now you want to convert this revolutions per second into RPM. So you will multiply this by 60. So this is 60 multiplied by F by 2. And now if you just want to write down this one, this can be also written as 30 F RPM. For 4 pole machine, the speed is given as 30 F RPM. That is whatever frequency you are applying multiplied by 30. Previous one was 60 F. Now, this is for 2 pole and 4 pole. We want a generic formula. Now, what was happening in 2 pole? In 2 pole, whatever F you are getting, you are just multiplying it by 60. Now, to have the 4 pole and 2 pole giving you a generic formula, what we can do over here, we know this is equal to 60 F divided by 2. Can we make it equal to 120 F divided by 4 over here? And what is 4? The number of poles. So instead of having F4 written over there, I can call this one as P. So this is now a generic formula giving up to you that 120 F by P is telling you the speed of the revolving magnetic field. And this speed is called as the synchronous speed. And why synchronous speed? Because I told you just in the very first part that synchronous machine has a constant speed. It will not change because I told you there will be a locking. So अगर ये 120 F by P की speed से move कर रहा है, you will get the same speed on the rotor. How? We will talk about that later on when time comes. So what this tells me, I have a formula 120 F by P, and this is called as NS. S is subscript over there, and we use it for synchronous also and rotor induction also. So now, if you are in Pakistan, you have number of poles here, you have NS here. If you have 2 poles, what is the speed of NS? Foot karo, 50 hertz. F is 50 hertz. 120 into 50 divided by 2, 3000 RPM. So you have 3000 RPM. This was actually 2. Why it has changed to? So 2. When you have 4 poles, what will be? 1500 RPM. If you have 6 poles, this will be 1000 RPM. If you have 8 poles, G. This is for Pakistan, remember, because in Pakistan frequency is 50 hertz. That's why I'm taking 50 hertz. If you're doing this calculation anywhere else, maybe USA, then it will be different. So the 8 poles, 750. Now, your induction machine, listen this very carefully. Your induction machine, if it is 2 pole, it will be having a rotor speed, which we will define as NR. We are going to call this as NR, and it will be close to this 3000 RPM. Not exact. Why? Because there is a speed regulation, as I've told you. और ये क्यों पीछे है वो भी हम डिस्कस करेंगे इन द नेक्स्ट लेक्चर. And if you have a 4-pole, you will be having 1500 RPM, close to that. Not exact 1500, कभी नहीं हो सकता. 1400, 1450, 1480 हो सकता है. Now, I don't know how many of you are enthusiastic about this machine's course, but try to find out the speed of your fans at your home. If you are talking about a ceiling fan, इसको छोड़ो ऊपर, इस पे जाके इसकी name plate rating पढ़ो, you will find out that the speed written on it is approximately 1485. This is telling you that you have a 4-pole inside this induction machine. It's not a 3-phase. Remember, it's not a 3-phase, but the principle is the very same. वो भी हम बात करेंगे in the next lecture. But here it's a 4-pole. And those of you who have a pedestal fan, आप तो खैर बहुत non-existent है, लेकिन pedestal fan if you have it because it's standing vertically, the speed is approximately 1000 or 750 RPM. So they have a little bit large number of poles. Now this also gives you one answer. If you are in Pakistan, the maximum speed you can achieve in Pakistan without a gearbox, 3000 RPM. क्यों? क्योंकि पाकिस्तान के अंदर frequency 50 Hz. Unless and until you change the frequency, number of poles P2 minimum है, इससे कम नहीं हो सकता, zero नहीं हो सकता. So the maximum speed possible in Pakistan is 3000 RPM without a gearbox. If there is a gearbox, certainly then you can amplify that speed. Torque will be less, but speed will be small. So if you have this one as 60, because your book is from an US author, so you are going to get approximately some different values over there. You are going to get 3600, you are going to get 1800 RPM. Gee, what about 6 and 8? Please do a calculator. Gee, come on. 6 into 120 into 60 divided by 6. 1200, I guess. What about 8 poles? Come on. 900. Now, the interesting thing, just a little bit idea about Pakistan. If you go to Tarbela Dam or Mangla Dam, the amount of poles, they are synchronous machine. They are not induction machine. They are synchronous generators. We will talk about that one. But the number of poles in Tarbela Dam or Mangla Dam is 36. Go over there, you can find. Now you can find out, corresponding to 36, what will be the speed. You can plug in the values and find out. That is approximately something 178 or something like that, RPM. So the point over here is this, that in Tarbela and Mangla Dam, the water flow is so large, that you are not getting speed over there. You 166, 166. So you are getting approximately large torque, but speed is small. We will talk about steam turbine power plants also. That's also a part of our course. We will talk about the hydel turbines, Tarbela and Mangla or any other power plant. But here, the point is that today we have talked about the revolving magnetic field over here, and you have to find out the speed by using 120 F by P. Your induction machine will be having a speed NR slightly less than NS. And for synchronous machine, if you have a synchronous machine, your NS will be equal to NR. Why? I told you there is going to be a locking. They are not going to have any speed regulation over here. Ajay ji, try to